Hello guys, welcome to the example aspect of linear first order differential equations. So we're going to begin with problem 1. Solve y prime plus 3y equal to x plus exponential minus 2x. So clearly you are seeing a dy dx, which is still the same thing as y prime, plus 3y is equal to x plus exponential minus 2x. So you can see that this conforms to the general approach for expressing linear first order differential equations, where our p is equal to 3, a constant, and our q is equal to x plus exponential minus 2x. So remember that to solve this particular equation, we needed to come up with an integration factor, mu, which is exponential integral of p dx, so that we'll now apply the formula y times integration factor is equal to integral of q times integration factor dx. So let's see how we can apply all this to get the solution to this problem. Okay, now the first hurdle is to get the integration factor, which in our case is mu is exponential integral of what is our p, or p of x. We have 3 dx, and if you evaluate this, you have exponential 3x. So when you're integrating for the integration factor, you don't need to put the integration constant. It's not necessary to put the integration constant. So we have gotten our integration factor to be what? Exponential 3x. So we're now going to put it in the formula straight up. You don't need to stress yourself too much. Just use the formula, and the formula is y, in this case, times integration factor, which is exponential 3x, then it's equal to is equal to q. And what is our q? Our q is x plus exponential minus 2x, and our integration factor is exponential 3x dx. Alright, so we have y exponential 3x is equal to integral of x exponential 3x, then plus exponential minus 2x times exponential 3x gives us exponential x when you obey the law of indices. So moving on, you're going to get y exponential 3x. So let me distribute the integration. Exponential 3x dx plus integral of exponential x dx. Now to evaluate this particular side, okay, to evaluate this particular side, you can go ahead and use your product rule of integration, which states uv minus integral of v du for an integral of u dv. Okay, you can go ahead and use it, but I'm going to show you a shorter method, and we're going to apply that method now. So assuming you want to integrate, this is a shorter method. You want to integrate x exponential 3x dx, and this method works for a combination of polynomials and exponentials with linear arguments. So the polynomials will be on this side, and the exponential will be on this side. Okay, so you're now going to differentiate the polynomial until it gets to 0, while simultaneously integrating the exponential onto the point where your differential gets to 0. So differentiating x, I'll get 1. If I integrate exponential 3x, I'll get exponential 3x over 3. Now if I differentiate 1, I'll get 0. And if I integrate exponential 3x over 3, I'll get exponential 3x over 3 times 3, which is 9. So this is where I stop. So I'm now going to do some kind of multiplication. So the first multiplication is going to be x exponential 3x over 3. Now the second multiplication is 1 times this term over here, or you're going to use a minus sign, which is just exponential 3x over 9 plus c. So after the multiplication finish, you put a constant of integration plus c here. So this is going to be the integral of this particular term over here. So So we can just write y exponential 3x is equal to, what did we get, x exponential 3x over 3, then minus exponential 3x over 9, then plus, let me leave c first. When we integrate this guy, we'll get exponential x, still exponential x, then plus c. So for these two integrals, both of them can have just one integration constant. Even if you want to separate the integration constant, maybe you get c1 here and you get c2 here, c1 plus c2 is still another arbitrary constant, which we can just call c, for instance. So at the end of the day, you're now going to divide through by exponential 3x to get y. So dividing through by exponential 3x, so you have 1 over exponential 3x on x exponential 3x over 3 minus exponential 3x over 9 plus exponential x plus c. So if we evaluate, we'll now get y is equal to x over 3 minus 1 over 9 minus 1 over 9 and plus exponential x divided by exponential 3x gives me exponential minus 2x, right? Then plus c divided by exponential 3x is actually c exponential minus 3x when you follow your law of indices. Okay, so we're going to factor out 1 over 9. So of course someone can leave his answer like this, but you can factor out 1 over 9. Let's do that together. So y is equal to 1 over 9. So you get 3x here, right? And minus 1 here, and you get plus 9 exponential negative 2x plus 9c exponential what? Minus 3x. Okay, so this 9c can be another constant. Let me just say a, for instance. So y is equal to 1 over 9 into 3x minus 1 plus 9 exponential minus 2x plus a exponential minus 3x. So this is a good way to leave your answer. Okay, so one thing is in ordinary differential equation is that there's no just one particular way of like always stopping all the time. So as much as you can do to stop at a good point, all the mathematical laws you've learned up till now, just try to apply them so that you can get a good answer. Okay, you can get a good place where you will stop. So let's move on to the next problem. Alright, welcome to problem 2. We want to solve 1 minus x squared dy dx minus xy equal to 1. So, solution. Now, look at this problem. We are given 1 minus x squared dy dx minus xy equal to 1. So it looks like a linear differential equation, and we can actually make it that way. Please take note, we cannot actually separate this linear differential equation, and the reason we cannot separate it is because of this guy over here. If you tried to see if you wanted to separate it, you'll be getting something like this: dy dx is equal to xy plus 1, and this xy plus 1 is not a function of x alone or a function of y alone. It's rather a function of x comma y. So it's actually a mixture of x and y. Okay, so the requirement for separable variable is that you should need to have something that you can separate, a distinct mixed function of x or a distinct function of y that you can actually carry to this side and to that side and so on and so forth. So this x y plus 1 does not afford us the liberty to separate the variables into either x or into y, because it's actually looking like a homogeneous combination of x and y. So this is actually a linear differential equation. So the first thing you need to do to solve this particular problem is to divide through by 1 minus x squared. So if we are dividing through by 1 minus x squared, this is what we are going to get: dy by dx minus x over 1 minus x squared y is equal to 1 over 1 minus x squared. Are we together? So if I want to make it linear, or if I want to express it in the linear form, remember the linear form, recall we have dy dx plus py is equal to q. So this is now dy dx plus minus x over 1 minus x squared y is equal to 1 over 1 minus x squared. So in writing this differential equation like this, you can see now that I've obtained an expression for p, and this is an expression for q. So we can now find our integration factor, mu of x, by saying mu of x is the exponential integral of minus p of x dx. So let's resolve this integral. It's looking like a challenge, but if you look at it very carefully, you won't have to stress yourself. Now consider this integral. Let's do it together. Exponential integral of minus x over 1 minus x squared dx. Now it's still the same thing as you saying exponential integral of, look at this denominator. The term in the denominator is 1 minus what? X squared. Has it mean we are differentiating this term with respect to x? What we are going to get is minus 2x. So you can as well say the d of 1 minus x squared is negative 2x dx. Okay, so d of 1 minus x squared is actually minus 2x dx. So is there a way I can actually make this numeric this particular place look like minus 2x dx? Yes, of course there is a way. All I need to do is to put a 1 over 2 outside first, then I'll now put what? A minus 2x over 1 minus x squared dx. So the 1 over 2 outside is actually to cancel the effect of introducing this 2, because 2 was not there before. Is that okay? So I had to introduce a countermeasure, so that whenever you introduce something, you need to actually introduce the reciprocal of that thing, so that the equation will be balanced, or the expression will be balanced. So mu of x is equal to exponential 1 over 2 integral of, so instead of you to have minus 2x dx, we have 1 over 1 minus x squared minus x squared. So in place of minus 2x dx, I can just have d1 minus x squared. So this makes it very, very easy to take from here. So mu of x, or mu, is now exponential 1 over 2. Then this is ln 1 minus x squared. Okay, remember when you're integrating 1 over something d something, your answer is ln something. Is that okay? So take note of this convention. So that's the trick that we'll be using to approach our problems. When you're integrating 1 over something d something, your answer is ln something. So that is exactly what we did to get to this point. So mu is now going to be exponential ln, applying the law of logarithm, 1 minus x squared raised to the power of half. And according to the rule that exponential ln f is equal to f, according to that rule, then exponential ln half 1 minus x squared is actually 1 minus x squared, or raised to the power of half, like this. So this is the value for our what? Mu. Is that okay? This is the value for our mu, which is 1 minus x squared raised to the power of half. So remember the formula. The formula to apply mu is y times mu is equal to integral of q times mu dx. So all we just need to do is to get what q is, from the linear form. So, and q, the q that we got, let's just trace it back to the linear form. This is our q, okay? So this is our q over here. Sorry, this is our q. 1 over 1 minus x squared. 1 over 1 minus x squared. So let's see how this goes. So we'll get 1 over 1 minus x squared. Then we now have 1 minus x squared raised to the power of 1 over 2 dx. So on this particular left hand side, it's just as if you're having 1 over a times a raised to the power of half, and this is going to be a raised to the power of half minus 1, and this is a raised to the power of minus half. So the right hand side, the argument of the integral in the right hand side can be expressed in this form: 1 minus x squared all raised to the power of what? Minus 1 over 2 dx. Is that okay? So what exactly does this mean? It means that y into 1 minus x squared all raised to the power of half is equal to the integral. When you apply the law of indices, of course, a raised to the power of minus half is 1 over root a. So we will have 1 all over root 1 minus x squared dx on this side. So if you go further to simplify, you get y into 1 minus x squared raised to the power of half is equal to, so this is a standard integral and corresponds to sine inverse of x, okay, plus c. Now you have to remember that when you differentiate your sine inverse of x, you're going to get 1 over the square root of 1 minus x squared. So remember this standard integration or differentiation, so that whenever you're integrating 1 over the square root of 1 minus x squared, you get your sine inverse of x. So this is what we have for c. So y at the end of the day is now going to be sine inverse of x plus c divided by what? 1 minus x squared raised to the power of 1 over 2. Or you can still write it as c plus sine inverse of x over root 1 minus x squared. So this is a good place to stop for this particular problem. So let's move on to another problem 3. Okay, this is problem 3. I want to find y given that tan x dy dx plus y is equal to sec x. Okay, as usual, this is a linear differential equation. All we just need to do is to divide through by tan x. So we get dy dx plus 1 over tan x y is equal to sec x over tan x. Now let's remember some identities. Sec x is equal to 1 over cos x, and tan x is the same thing as sin x over cos x. The reciprocal of tan x is the same thing as cos x over sin x. So we're going to keep these identities in mind as we proceed. So let's just resolve a little. Dx plus, this is cos x over sin x of y is equal to sec x being what? Sec x being 1 over cos x, and tan x, the reciprocal of tan x being cos x over sin x on this side. So if we simplify, we're going to get dy by dx plus cos x over sine x of y is equal to 1 over sine x. Now at this point we have our dy dx plus p y is equal to q. So in this case p is cos x over sine x and q is the reciprocal of sine x, which some people might call cosec x. Alright, so we already know that our integration factor is exponential integral of what? P dx. So which in this case is exponential integral of cos x over sine x dx, which in this case, if you look very carefully, is exponential integral of d sine x 1 over sine x. So why did I say this? Because consider you wanted to differentiate sine x with respect to x, you're going to get cos x, right? So anytime you see d of sine x, it's still the same thing as cos x dx. So in other words, we can always replace a cos x dx. You can replace any cos x dx with d of sine x. Okay, so our mu, let me write it clearly, is exponential integral of, instead of cos x dx, I can just leave it as d sine x. So remember our trick. Our trick is integral of 1 over something d something is equal to what? 1 over something d something is equal to ln of that thing, right? So our mu is equal to exponential integral of 1 over sine x d sine x, which is ln sine x. And we also have to remember that exponential ln f is equal to f. So exponential ln sine x evaluates to sine x. So this is our integration factor. So after getting our integration factor, then the formula y times integration factor is equal to integral of q times integration factor dx. So y times sine x is equal to integral of q. Our q was 1 over sine x times integration factor was sine x. Is that okay? So you can see that y sine x will be equal to integral of 1 dx, and y sine x is equal to x plus c. So at the end of the day, y is still the same thing as c plus x over sine x. So you can actually stop here for this particular problem. So I hope there was no much issues on this one. Let's move on to the next one. Okay guys, let's move on to problem number 4. Now problem number 4, we have solve this particular differential equation, evaluate dz dx plus 3z x inverse is equal to 3 cos x over x cubed. Okay, so to solve this differential equation, all you need to do is, of course, to still write it plus 3z x inverse is equal to 3 cos x over x cubed. So they are just trying to mess around with us in terms of the variable. You're seeing z here and you'll be wondering how is this, but don't be scared at all. It's still the same underlying principle. Once you are able to apply the same underlying principle, then you can be able to solve this problem without any hassle, without any stress. So if you express it in the general form, let me say the general form is dz dx, general form dz dx plus p, okay, z is equal to q. Okay, so this is the general form for a linear differential equation. So we'll have dz dx plus p is 3. Now x to the power of minus 1 is still the same thing as 1 over x. So this 3 z x to the minus 1 is 3 over x, then z. Now have 3 cos x over x cubed. Alright, so let's see where this takes us. Of course, then our p in this case is 3 over x, and our q in this case is 3 cos x over x cubed. Now our mu is exponential integral of what? P dx, right? So we have exponential 1 over 3 integral of, exponential 3 integral of 1 over x dx. This gives me an exponential 3 ln x. This gives me exponential ln x cubed, and this is x cubed in the long run. So you now use the formula z times integration factor is equal to integral of q times integration factor dx. Okay, so using this formula we have sorry about all of those. We have z multiplied by integration factor is x cubed. X cubed is equal to integral of q. Q is cos x over x cubed multiplied by our mu is actually x cubed. Is that okay? Then dx. So you can see now that x cubed can cancel out x cubed. So you have zx cubed is equal to integral of cos x dx. So z x cubed, when we integrate cos x, what do we get? Yes, that's right, sin x plus c. So at the end of the day, z is equal to c plus sin x all over x cubed. So I can leave it here like this. So this is about this problem. Alright guys, welcome to problem number 5. So for problem number 5, we have to solve y prime plus y cos x is equal to 5 exponential cos x. And this is an IVP because an initial condition was given to us that y of pi over 2 is equal to -4. So we're going to begin. Let me change y prime to dy dx plus, let me bring cos x first before y, and is equal to 5 exponential cos x. Okay, so to solve this particular problem first of all, of course, we already have the general form of evaluating differential equations. We have y dy dx plus py is equal to q, and in this case our p is cos x. For cos x, remember we mean cos x over sin x, and our q is exponential cos x, 5 exponential cos x. So we are going to start by evaluating the integration factor, which is exponential integral of p dx, which in this case is our exponential integral of we have cos x over sin x, sin x dx, and this is going to give me exponential integral of, if you follow that our normal approach, you're going to get what else? What are you going to get? Yeah, that's right. You're going to get 1 over sine x. Then you now have d sine x. Is that okay? So our mu is equal to exponential lim sine x, which is equal to what? Sine x. Okay. Okay, sorry about that. I just needed to check, double check something again. So having gotten our integration factor, of course, straight to the formula. Y times integration factor should be equal to integral of q times integration factor dx. So y times integration factor is now going to be integral of q, which is 5 e to the what? Cos x, then integration factor is sin x dx. Okay, so let's figure out how to integrate this one together. So this is not so far-fetched. The main thing that you need to observe in this particular integral is this term over here, cos x. So let's do it together. Y sin x, y sin x is equal to 5 integral of exponential cos x dot sin x dx. Now, assuming you want to differentiate, take the argument of your exponential term here. Assuming you wanted to differentiate that cos x with respect to x, you're going to get minus sin x. Is that not correct? So anytime we have d of cos x, you agree with me that d of cos x is minus sin x dx. So if there's a way I can introduce a minus sin x dx to this place, which of course there is, it will simplify my integration procedure. So I just have to put a minus outside first of all, then I now have exponential cos x, then minus sin x, then dx, like this. So this minus sign has now cancelled out the effect of this one inside. Okay, so that minus times minus will plus, and you can get back to the original form. here. So now that we are seeing minus sine x dx, we can replace it with d of what? Cos x. So you have y sine x is equal to minus 5 integral of exponential cos x d cos, sorry, let me write it well, d cos x. Okay, and the rule is still simple. When you're integrating exponential something with respect to something, you still get what? Exponential something, okay, plus your integration constant. Okay, so this is the power of this method. It's called integration by substitution, and it's still a blend of chain rule. So you might want to actually refresh your knowledge of chain rule and integration by substitution so that you can understand some of these techniques for integration. So y sine x is equal to negative 5. Then integral of exponential cos x d cos x is actually exponential cos x plus c. So you can now see that our y is c minus 5 exponential cos x over sine x. So we can actually leave it here. Okay guys, now after we've gotten the solution for y, we need to apply the initial conditions given to us. The initial conditions given to us on the question was y of pi over 2. Sorry, let me just create a space for it over here. So y of pi over 2 is equal to minus 4. So it means that whenever y is minus 4, x has a value of pi over 2. So if we substitute it into this equation over here, to substitute it into this equation, we'll have minus 4 is equal to c being the arbitrary constants. We have 5 exponential cos pi over 2 divided by sine pi over 2. Now cos pi over 2 is 0 and sine pi over 2 is 1. Cos pi over 2 is actually cos 90, okay, and sine pi over 2 is sine 90. So you will have minus 4 is equal to c minus 5 exponential 0 over 1. If you resolve this particular problem, we are going to get c to be actually minus 4 plus 5, which is equal to 1. Is that okay? So it tells us that our solution is y. Our solution is y is equal to 1 minus 5 exponential cos x over sine x. So this is our particular solution. For the initial value problem. Okay, so this is the general solution over here, general solution, where you are giving the solution in terms of arbitrary constants. So once you apply the IVP given to you, the initial conditions, you now arrive at the particular solution. So okay, we can now move on to another example now. Okay guys, here we go with problem 6. Solve the equation 1 plus x squared and dy dx plus 3xy is equal to 5x. So how do we go about this? So 1 plus x squared dy dx plus 3xy is equal to 5x. So to solve this particular differential equation, as usual, you need to divide through by what? Good, that's correct. Divide through by 1 plus x squared. So the y dx plus, we have 3x over 1 plus x squared, all together, y is equal to 5x over 1 plus x squared. So of course you agree with me that my p is now 3x over 1 plus x squared, and my q is 5x over 1 plus x squared. So our integration factor mu is going to be exponential integral of p, right, which is 3x over 1 plus x squared dx. So let's solve along. So this is exponential 3 integral of x over 1 plus x squared dx. So if you consider the derivative with respect to x of 1 plus x squared, you get 2x. Is that not so? So in other words, d of 1 plus x squared is equal to what? 2x dx. Is that not correct? Now what we have in the numerator position is x dx. So maybe if there's a way I can introduce 2, then I could be able to replace some things appropriately. So I'll have my mu to be exponential. So this is what happens: 3 over 2, then 2x dx over 1 plus x squared. So our 2x dx can now be replaced by what? 1 over x plus x, 1 over 1 plus x squared. So our 2x dx is now replaced with what? d1 plus x squared. Is that okay? So instead of you to have 2x dx, you're having d1 plus x squared. And remember, this whole part in the integral now, what you're seeing here in this part in the integral will conform to what I've established. I've been establishing this integral of 1 all over something d something is still ln something, okay, ln something. So this technique of integration by substitution is very, very, very important, as you have seen in this particular case. So our mu, which is our integration constant, integration factor, becomes exponential 3 over 2 ln 1 plus what? X squared, right, which is exponential ln 1 plus x squared raised to the power of 3 over 2, which is 1 plus x squared raised to the power of 3 over 2. So the reason is exponential ln f is equal to f. Is that okay? So we can now go straight to the formula. That's y times integration factor is equal to integral of q times integration factor dx. Okay, so let's just recall what our q is. Q is 5x over 1 plus x squared. So let's tackle this problem now. So our y multiplied by 1 plus x squared raised to the power of 3 over 2 is equal to integral of 5 over 1 plus x squared. Then you now have to multiply it by 1 plus x squared raised to the power of 3 over 2 dx. Is that okay? So let's see how to go about this. Let me just be sure of something. Oh, 5x. Okay, it's actually 5x over 1 plus x squared. So we have y 1 plus x squared raised to the power of 3 over 2 is equal to, so if you do a raised to the power of 3 over 2 divided by a, it's still the same thing as a raised to the power of 3 over 2 minus 1, which is a raised to the power of 1 over 2. Is that okay? So the right hand side simplifies to 5x, then 1 plus x squared raised to the power of half dx. Is that okay? Then you have y of 1 plus x squared to the 3 over 2 is still the same thing as okay, so let's take this integral gradually. We are still going to use the same technique. So you have 5 integral of, so I'll bring this one first of all, 1 plus x squared, then 1 over 2, then I have x dx. Of course, remember d by dx of 1 plus x squared is equal to 2x. So d of 1 plus x squared is equal to what? 2x dx. So remember this. Now we have y plus 1 plus x squared 3 over 2 is equal to 5. So I want to make this 2x dx, okay, in this form, so that I can replace 2x dx with d of 1 plus x squared. So to introduce a 2, I have to introduce a reciprocated version of 2 as 5 over 2, then integral of 1 plus x squared half, then 2x dx. Is that okay? So since I have introduced it in this particular form, what you just need to do is to replace the 2x dx. Replace the 2x dx with what exactly? You replace it with d of 1 plus x squared, d 1 plus x squared. Okay, so they are trying to tell me that the integral of something raised to the power of 1 over 2 d something, I just need to apply that rule, and I hope you remember the rule. What does the rule say? The rule of integration. So it will be something, sorry about that. It will be something raised to the power of 1 over 2 plus 1 over 1 over 2 plus 1. So which gives me something raised to the power of 3 over 2 over 3 over 2. Like that. Is that okay? So I'm going to get y into 1 plus x squared raised to the power of 3 over 2 is equal to 5 over 2. Then when we integrate this side, what we got was 1 plus x squared raised to the power of 3 over 2 divided by 3 over 2 and plus c. Are we together? So y into 1 plus x squared raised to the power of 3 over 2 is equal to, so 5 over 2 divided by 3 over 2 is actually going to give you 5 over 3, right? 1 plus x squared raised to the power of 3 over 2 plus c. So at the end of the day, if we divide 2 by 1 plus x squared raised to the power of 3 over 2, we get y is equal to 5 over 3 okay, into 1 plus x squared raised to the power of 3 over 2 plus c all over 1 plus x squared raised to the power of 3 over 2, which someone can still evaluate as c plus 5 over 3, or sorry, you can still evaluate it as c into 1 plus x squared raised to the power of minus 3 over 2, then plus 5 over 3, like this. So this is our y, c into 1 plus x squared to the minus 3 over 2 plus 5 over 3. So this brings us to the end of solutions to differential equation by the linear method. So I know we did a lot here, and some things may seem strange to you, but I can assure you that you should pause the video and try to meditate on some things, meditate on some steps, and feel free to drop comments, drop questions whenever I see them. I will attempt and attend to your questions. So I hope you learned a lot from this video. Thank you for watching. Thank you for staying up to this time. Don't forget to share, like, subscribe, hit the notification button to stay updated. So in next video we're going to be considering homogeneous differential equations. So stay tuned. Peace. Stay safe.